Ladies and gentlemen, greetings. In this video I would like to talk to you about implicit differentiation and its applications. I checked multiple online tutorials, however none of them were offering quite the explanation that I have in mind. So I decided to make my own video for this, and I hope you'll find this useful. But first things are first, in order for you to get the most out of this video, I expect you guys to be pretty well acquainted with these three rules of differentiation, chiefly the power rule, product rule, and the chain rule. And because of how important the power rule is for our further discussion, I would like to briefly revisit it here. So power rule tells us that given a variable raised to the power of n, we can certainly take its derivative, and that's going to be pretty easy peasy because the power of n is going to come up front to hang out, variable is going to stay there, and its new power will be given to us by the formula of n minus 1. Specific consequence of this formula shows up right here, which tells us that the derivative of variable x with respect to x is going to totally obey the power rule, and at the end of the day it's going to result in a numerical answer of uno, number 1. So the derivative of x with respect to x is going to be a scalar answer, and it's going to equal to 1. It's a pretty important result that will become handy in a few minutes, so let me encapsulate that into a black frame. And from here, let's just jump straight into it. Let me give you the secret ingredient right away. So suppose we are asked to find the derivative of x squared, like so. And I think it's a pretty easy task for most of you. You probably are sitting on the other side of the screen and you're shouting out with glee saying, I know exactly what is going to be the answer to this question. So you would be correct in saying that the answer is going to be 2x, that's right. But there is one little detail that I want to draw your attention to, and then from now on, so the trick that's going to put you in the right mind frame is to append at the very end the variable that you were just taking a derivative of with the prime sign at the end, like this. Okay, you guys with me on that? All right, that was the secret. Okay, let's try another one. We didn't solve this by any means, but we just executed what we set out to do. Okay, so let's try another one. Now let's try to find the derivative of t cubed. If you'll notice, according to this power rule, we have a variable raised to the third power, and if we're going to pull the trigger on the power rule, we will get a non-surprising answer of, right, 3. We're going to come up front, excellent. Then it's going to get multiplied by t squared. But there is one tiny little thing that we're missing here, namely the t prime, like this. Now let's try and find the derivative of z to the 4th, and if we are tasked with this, I think it's going to come as no surprise to all of you that power rule is going to result in 4z cubed, but what did we agree on doing? We agreed on appending that variable with the prime at the very end for our own bookkeeping, so to speak. How do you guys feel about this? I hope this is sinking in. Okay, and now let's try and step it up a notch. So now let's suppose we are presented with the more formidable mathematical problem of finding derivative of such a product. Now, in order for us to execute this, I wanted to briefly remind you how the product rule looks like. And product rule is given to us by the following formula. If we have a product of f and g, and we are tasked with finding its derivative is going to be a sum of two terms right here. First term is going to consist of derivative of f times g, the original g, and the second term is going to consist of derivative of g times the original f. Okay, so now let's carefully try and apply this product rule to this problem at hand. If we execute this correctly, we're going to have something like this. Z to the 4th prime times t cubed plus z to the 4th, we're going to let it be because we already differentiated it in the previous term, and in turn we'll have to multiply it by the derivative of t cubed. Okay, if you guys want, please pause this for a minute and carefully finish this line. Mind you, please don't forget about these primes. I think our previous work here on the left would help us out. But yeah, pause the video and try finish this line on your own, and I'm going to come back to you in a minute and we're going to compare notes, okay? All right. All right, guys, I'm back. I hope it went pretty well. Here's what I've got. If I execute the product rule correctly, I'm gonna have something of this sort on my hand, and if I'm gonna take care of parentheses and combine what I can, I will end up having something like this. I know to many of you this might look, well, a little unsatisfying, but in my eyes, guys, if you were able to go from here to here, I think I would be a happy camper. What matters to me the most right now is that you correctly remembered to multiply things by z prime and t prime wherever that was appropriate. Okay? All right, so let's try something similar to what you're going to see on your homework or on your test or quiz. So suppose we are presented with something like this. Given this equation, we are asked to find dy dx. However, guys, I would like to stress to you that dy dx is also known, aka, as y prime, right? We don't know still the expression for y prime, but at least we know that we are on the hunt for y prime. Okay, there are two ways of doing this, explicit way and an implicit way, and since the video is talking about implicit differentiation, we're going to focus on the implicit side, and actually, quite frankly, implicit differentiation is simpler. So here's what I recommend. Let's take a derivative of each term individually. Derivative of x squared, derivative of y squared, derivative of 4, like this. But in fact, if we do everything correctly, here is what we're going to end up with. If we're going to take a derivative of x squared, naturally we're going to have 2x times, what do you think I'm going to type in next? Right, x prime, plus 2y, you're not going to be shocked by this one, right? And on the right-hand side, well, on the right-hand side, we're going to get a good old-fashioned 0. This is it. Here we have it. Here's our differentiation in its full glory. And now I would like to capitalize on this formula right here. What is the x prime again? X prime is effectively 1. So we can rewrite this equation in a slightly simpler way. 2x, right, plus 2y, y prime, still there, equals to 0. All right, so from here, you're on the home stretch. Your goal is to solve algebraically for y prime. All right, we're going to outsource the algebra to you. I'm just going to fast forward a little bit, and here is what I'm going to get as my final answer for y prime. Ta-da! Here we have it. So guys, my goal is for you to be able to connect the dots and to see how you can go from an equation like this, perform your differentiation. Please, 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 pinky promise me you're not going to forget to multiply by variables with prime right immediately after you're going to take your derivatives. Okay, and then I'll be frank with you, for the sake of Calc 1, it is quite okay to recognize that x prime, which is derivative of x with respect to x, is 1. Another, well, not strictly speaking mathematically kosher way of thinking about it, but an easy way to remember this, dx divided by dx. It's not a strictly speaking division, but it helps to remember. Dx over dx is going to be 1. You can visually recognize that. That's an easy way to remember it. The goal is to recognize your equation, perform your implicit differentiation, then see where it's appropriate to substitute 1 in place of x prime, and algebraically solve for y prime. And ta-da! Here's an answer. Okay, let's try another one, shall we? All right, suppose we have something of this sort. Let me zoom in a tiny bit. Okay, given this equation, we are once again asked to find dy dx, aka y prime. So in this specific case, once again, we could have gotten about it in a slightly different way. We could have rearranged this equation to get y by itself, and then we could have pursued y prime, but that would require an explicit application of derivatives, and the benefit of this approach would lie in the fact that y prime would be given to us purely in terms of x's. But that's not our goal. Our goal is to find y prime no matter the cost. We don't care. This is not a beauty contest. It doesn't have to look real pretty. It just has to be done. And if it has to be done, we can ditch explicit differentiation and we can proceed using implicit differentiation method. Okay, so the plan of attack is extremely straightforward, guys. Implicit differentiation allows you to take derivative of each term, so to speak, individually. So x squared y will gonna get its own differentiation, y will gonna be differentiated, and then number 7 will also gonna get differentiated. If we're gonna do as we just preached, we're gonna have this result in our hand. Product rule, we've seen how to manage something like this before. X squared prime times y plus x squared times y prime, the derivative of y as a variable. That's a straightforward application of the power rule. And on the right hand side again, we're going to have y differentiated, and derivative of 7 is going to clearly become 0. Okay, so I hope it's so far so good. Let's bring it one step further. Applying power rule yields 2x times x prime. We agreed every time we differentiate we must follow up with that letter prime, okay, times y plus x squared. Well, derivative of y as a variable would be 1, but because it's implicit differentiation at play here, we must multiply further by y prime. And the same exact carbon copy, same exact argument shows up on the right hand side here. Derivative of y as a variable will be 1, right? But implicit differentiation, we're going to have 1 times y prime. Okay, all right. Let's take another step forward, and if we do that, now we are tasked with combining like terms. And what I mean by that is that bring everything that involves y primes to one side and keep everything else that does not involve y primes on the other side. Okay, here I did 2 steps in one line. I combine like terms and factor out y prime, and now we are again an arm length away from our answer. Our goal is to find y prime. Well, we can easily accomplish that by dividing left and right here by 1 minus x squared. And I think this is going to be a good enough final answer. Okay, guys? All right, let's try just a few more to solidify what we've seen here. Now, let's consider that we are given an equation for the folium of Descartes. And now what we are going to do, we're going to increase the complexity of the problem that we're tackling once more. Okay, so we are now presented with an equation, and we are asked to find equation of the tangent line at this point, as well as an equation for a normal line at the very same point. I think many of you probably have a fairly good idea on how to proceed, but just in case, let's walk through this together. First step will be to find the expression for y prime. Let's apply implicit differentiation to this formula. And by the way, unlike the previous couple examples, in this case, it's mathematically impossible to separate y variable by its lovely self, and therefore the answer must contain y's, regardless of our sentiment. Okay, so let's see what we can do here. Let's apply implicit differentiation, and that will enable us to take derivative of each term of this guy, of this guy, of this guy, and if you really even feel adventurous, you can take derivative of 0. You're naturally going to receive 0, but mathematically that's a legit way of going about it. All right, so if we will take the next step, we're going to get something like this. And guys, again, I encourage you to pause the video for a second and hammer out the next line. Okay, all right, give this a try. Okay, guys, and at this point, please help keep me honest and help ensure that I'm not messing anything up. So my next step yields this. What do you guys think? Are you on board with that? Another step forward will gonna bring us to something like this. And notice at this stage, we no longer have any x primes dingling around. And if you're still wondering why, let me refresh your memory. It's because of this identity that indicated that x prime derivative of x with respect to x is always axiomatically going to equal to 1. That's what allows us to replace x primes with just multiplication by 1, which is mathematically transparent. And while we're at it, we started to combine like terms, and we started to put everything that contains y prime on one side and everything that does not contain y prime on the other side. Which segues us nicely into our next goal. And our next goal is going to be to algebraically solve this line for y prime. If my algebra didn't fail me, we're going to end up with an equation of this sort. And yes, you can notice that in theory, you could have factored out a common factor of 3 from numerator and the denominator and cancel them out, but for the sake of this discussion, common factor of 3 is inconsequential, so I'm not going to bother. Reason why I think we should give ourselves a pat on the back is because from calculus point of view, this is it. This is mission accomplished. But I can also almost hear some of you asking that at this stage, okay, why is this important? Why was this worth our while? And in that case, I'll say, well, I'm glad you asked, because there is a pretty sizable silver lining coming your way right about now. So substituting 2 for x and 1 for y yields this expression. Y prime is going to, at the end of the day, equal to 15 over 12. So how easy was that, huh? Easy peasy. Dare I say plug and chug. Okay, so we're almost there on the quest of answering our question number 1, namely to find an equation of tangent line at the point 2, 1 of this graph. And now, since we have the coordinate of a point and the value of the slope, I think you can basically see the writing on the wall. So to me, it sounds like it's going to be only fair if we use the point-slope equation of the straight line, like this. So here's our canonic form of the point-slope equation of a straight line. And if we're going to substitute numerical values for all the letters that we know in this equation, we, my friends, will end up with this guy. And if we're going to perform a little bit of further algebraic simplification, it looks like our equation of the tangent line to this graph at the point 2, 1 is going to be given by formula y equals 5x over 4 minus 3 halves. But wait, there is more. This is about to get even better. Let's bring this problem to its ultimate extent by answering question number 2. If we know the value of slope m, we can very easily, courtesy of our pre-calculus days, find that the value of slope of the perpendicular line to y will be a negative inverse of 15 halves. So negative reciprocal of 15 halves is going to be given to us by the value of negative 12 fifteenths, right? So if we were to revisit our canonic form of the point slope formula of the line, good news is we're still operating with the same point of x equals to 2 and y equals to 1, right? So our value of y naught and x naught remain the same, and our value of m perpendicular, so to speak, is already also known. Guys, we are now ready to segue from our generic formula into something more mathematically concrete. And voila, here's what we're going to have. If we're going to do a little bit of cleaning up, combine like terms, and bring all the constants to the same side, we're going to end up with this expression. But guys, you don't have to take my word for this. I think seeing is believing, right? So let's go to Desmos and take a quick peek so you guys can be the judge. So here's our volume of Descartes right here, right? And what did we say was our equation of the tangent line? Oh yes, that's right. It was given to us by formula of 5x over 4 minus 3 halves. Well, let's take a closer peek. Here it is, 5x over 4 minus 3 halves, if I'm going to turn it in. Oh, would you look at that. This line appears to be exactly tangent to this graph at, let me zoom in on that, 2, 1, right? All right, and since we're not too far away from it, let's turn on this second equation and see if the line that's produced from it is indeed going to be perpendicular to the blue line. All right, look at this. So there you have it, guys. You can see for yourself that blue and green lines are exactly perpendicular, aka orthogonal, aka normal. Those are the three equivalent terms. They all mean the same thing. They mean that the blue and the green intersect at the 90-degree angle. And since blue is tangent to the curve, then line that's perpendicular to the tangent is also, by extension, is perpendicular to this red curve. All right, guys, so I think this is it. I think we can now officially say that we've answered everything that was asked of us in this comprehensive problem. So, ladies and gentlemen, I truly hope you found this useful. Thank you for watching and happy learning. Thank you, guys. We'll see you. Bye-bye.